I don't know if it's like the right number, but you have certain stuff.
Well, I'll say is one, stick to base variables, stick to like just volts. For the partials, it's just straightforward partial derivatives.
Yeah, I got it. But like for what values do you use for like plugging in stuff?
So you see this.
Yeah, I'm just going to use it.
Okay, so the U is the uncertainties. So for example, U for R1, R2, and R3 is plus or minus 0.1% of 20. So it's going to be
Right now,
Yeah.
would be the U, and you just plugged it in there. So it'd be the partial times that value, or partial squared times that value squared.
Yeah.
You run through it.
Yeah, my question is like, what do you do for like the strain, like for number 3 in the denominator graph?
Okay, let's start, everyone.
Would you have it there?
Here is the daily lecture summary that I advise you to look at every day. And still, when I talk to students, some even did not notice excellent resources that are made available to all of you. And so let me illustrate immediately. You know, the structure of my daily lecture summary is always the same. Let me zoom out so that. Okay, so there's always at the beginning some reminders. Okay, at the top, and then the lecture notes, and then towards the end there would be the video of the lecture, the audio, and my handwritten notes that I annotate after class. And this is a very important resource that I really advise you to really make use of it, because the reason is that I noticed that when students took notes, they only copy down what is written either on the board or what I wrote on the computer tablet, but not the words that I say. Okay, and the words is like 50% of the content. That's very important. And so what I did is that after class, I annotate with the red color there, typeset with red font. So you see it looks very different. You can watch the video and compare with my handwritten notes with annotation after class. And this is very important for study. Okay, if you miss something, everything is written down. It's also recorded in video, but you know, sometimes reading strongly complement what is on the video. Okay, so that's a very important message there. All right, so let me zoom in. So here the Michael already passed out the signature sheet. Let me bring up my mask here. And I also watched the video myself, you know. So I learned that I should not make the mask too narrow, because then the focus of the camera would be difficult. Okay, there are 2 handouts that you may want to pick up for future lectures here. 2 handouts, 4 pages on one. If you prefer to have 1 page on one, like Kevin of Team 7, then you can always print out on your own. But here, you know,
Is that an active learning credit? You said my name.
Okay. I have already talked about my handwritten notes with my annotation after class. Okay, so now I continue, and you see at the beginning of class I always bring up my handwritten notes from the previous lecture for continuity. You know, it's quick refreshing of your mind of what we did, and so that we move forward. Okay, for example, so yeah, we have gone through all this. You see, I mean, all this I didn't write in real time. I did this after, the annotation was done after my lecture, and it's very detailed. Okay, so I have shown to you that the stiffness matrix can be decomposed into this product of 3 matrices. In fact, gap phi or big phi, lambda is a diagonal matrix with the eigenvalues, and the inverse of gap phi. Okay. Quick active learning credit question or critical thinking question, just to connect you to what is on this handwritten notes itself and what I said in the previous lecture. If you went back into what is displayed when you use Wolfram alpha, okay, what did I prove? What did I show? Of course, what is shown in Wolfram alpha are not useless information, right? All the information here must have some usefulness. So what have I proved? Let me probably now it's easier to bring up my lecture notes on a bigger PDF viewer. So that's Sumatra PDF, since I can zoom in and zoom out much easier than the Google viewer. Okay, so essentially here, just to initiate, I did that, right? That is just the stiffness matrix, the determinant, I did that. The inverse, the inverse of the stiffness matrix, I did that. For the eigenvalues and eigenvectors, I asked you to accept so that we move forward. So what did I prove in the expression that I showed to you? Big phi, lambda, big phi inverse. What did I prove, Brennan?
The diagonalization.
Very good. That part here. We have completed this part. Okay, the diagonalization of the matrix M, and in our case we call the matrix K, or the stiffness matrix. Okay, so so I have proved completely this part with different notation. Once more, M is K for us, and S is essentially the big phi, and S inverse is big phi inverse. Okay, and J is what I call lambda. All right. M is K again. M is the same as this matrix K. All right. So that's a quick review there. And so characteristic polynomial, we do that soon. So whatever I put as a question mark means you accept for now and focus on the diagonalization, and we'll do that soon. Okay. So that's what I did at the end here. Okay, right. And I also showed you the orthogonality between the eigen vectors. Extremely important. Keep that in mind. So here, the inverse. This is a 2x2 matrix. So the inverse is relatively simple. But when you go to even a 3x3 matrix, inverse or even the computation of the determinant is not that simple. It gets really more complex. I just don't have time to show to you now. But take my word for that. Inverse is very, very time consuming. Even if you do by hand for 3x3, you will make mistakes if you're not careful. So, and then when you talk about a matrix that is size 1 million by 1 million, the inverse is prohibitively expensive. So if you can avoid the inverse, it's much more powerful. And so here is how you avoid the inverse. Okay, and so let me bring up my notes for today. First, the eigenvectors. Make sure that I turn this off. The eigenvectors can be normalized. Okay, so you have phi 1, which was 1, 1. And when you normalize, let me call that phi 1 bar. That's 1 over square root of 2 phi 1. Okay? Because the norm or the length of the vector phi1 is 2, right?
Is that 1 over square root of 2?
1 over square root of 2, yes. Because the length is the length square is 2, so the length is square root of 2. Okay. And so similarly for phi2, so phi2, you see that all you need is to replace the index. Okay, and let me move this out by 2. There's a minus here, so the length is also square root of 2. Okay, so now you can define the the next question is whether phi bar 1 and phi bar 2 remains to be eigenvectors. Okay, so here is a general theory. Let's say if phi1 is an eigenvector, you know that k bar k times phi1 equal to lambda 1 phi1, right? Now, if you multiply phi1 by any number, let's say epsilon in general, right? So a scalar, that is, if you multiply phi1 by a scalar, let me leave some space here. And squeeze in epsilon. Where epsilon is a scalar, any scalar, and call this new vector phi bar or phi hat, just to distinguish from phi bar up there. Phi 1 hat, and this is phi 1 hat. The hat is just to say that phi 1 hat is equal to a scalar epsilon times phi 1. Okay? Epsilon can be anything, can be minus 10, minus 100, 1,000, 1 million, doesn't matter. So what you see here is when you multiply an eigenvector with any number, it is again an eigenvector, right? With the same eigenvalue. Okay? With the same eigenvalue. So now let me put the hat on with a different color so you see that. So what's the commonality between phi 1 hat and phi 1? Well, they are collinear. Okay? These two vectors are parallel to each other. The only thing that is different between phi 1 and phi 1 bar is just the length. Okay? So therefore, there are infinitely many eigenvectors. Okay? You just multiply. If you can find one eigenvector, you can multiply that by any scalar to create infinitely many eigenvectors. Okay? As long as they are pointing in the same direction. So from this lesson, clearly, when you normalize the eigenvectors, so now let's put the bar as shown above. So let me zoom out so that you can see both, everything together in one screen. That's the normalization, right? What does it mean, normalization? Why did I divide by 1 over square root of 2? To make any active learning. Okay, let me bring in some new. What is your team number?
7.
Team 7, and the name?
Nick.
Nick. Okay. I know Kevin is very active, so let your teammate Kevin.
I really am, bro.
Have a chance. Okay, so Nick, team 7, what is what is the length or the magnitude of phi 1 bar and phi
Well, you're taking the dot product to normalize it.
yeah, so yeah, we did that, right? We just divide the vector phi 1 bar, that's right, divide phi 1 by its length, by the length of phi 1. So what would be now the length of phi 1 bar? That's the question.
It would be 1.
Phi 1 bar, the length of phi 1 bar and phi 2 bar. What would be the length of phi 1 bar and phi 2 bar?
Yeah.
Unit.
1?
It's a unit vector.
It's a unit vector. Okay, that's what I
Okay.
thought.
Phi 1 bar and phi 2 bar are unit vectors. That's what it's called normalization. Normalization means make it into unit vectors. Okay, so the same thing here, you get also the same thing for phi 2, right? Whatever that we did here with phi 1 also is valid for the other eigenpair. An eigenpair is a pair or a couple of eigenvalue and corresponding eigenvectors. Okay, so let me just delete the index 1 and replace the index 1 by the index 2. Okay, then we can introduce a new matrix big phi, and the new matrix big phi now would contain both phi bar 1 and phi bar 2, right? We call that big phi before. That's the matrix of the eigenvectors, was defined as the matrix in which you had phi 1 and phi 2 as the two columns. Okay, so now similar to this matrix, we define the matrix big phi bar. That's the matrix also of the eigenvectors, but now the eigenvectors had been normalized, had been made into unit vectors. Okay. Now this phi bar here, and recall that what was the matrix of phi, the matrix big phi in terms of the numbers. Recall that the first eigenvector is 1, 1, and the second eigenvector was 1 minus 1. So now very similarly, you know, there's a common factor 1 over square root of 2, right? So essentially you have 1 over square root of 2 times this same matrix here, because that's phi 1 and phi 2, right? And therefore you see that the big matrix, you know, this matrix phi bar or cap phi bar is simply equal to 1 over square root of 2 multiplied by the matrix cap phi. Okay, that's the relationship between the two matrices, cap phi bar and the matrix cap phi. Okay, so now let's look at the inverse. Okay, you can verify because I already gave you the formula for the inverse. This is a 2 by 2 matrix, so I will not go through the details again. I did that last time, but you can verify that the inverse of phi bar is its transpose. Do that as a home exercise. May even appear in the exam, so please do that. Okay, what I was saying is the following. Let me use a different color so that you can see clearly the inverse. Right, this is the inverse of big phi bar is its transpose. Okay, whereas if you did not have the bar, meaning if you did not normalize the eigen vectors, then the inverse of big phi is not its transpose. Okay, you can verify this also. It's very important. Very important to be able to do the inverse, the exact inverse of a 2x2 matrix without using the calculator. Okay, it's very simple. This is very important. Now, when you get to large matrices, even 3x3, you save a lot of computation if you knew that the inverse was the transpose. Believe me, even taking the determinant of a 3x3 matrix is not simple. Okay, it's a beautiful theory. Unfortunately, I don't have time to go through the theory of matrices like I mentioned last time. But take my words. Now, if you go to 100 by 100 or 200 by 200 and then 1 million by 1 million, this is computing the inverse is prohibitively expensive, meaning time consuming. Taking the transpose is nothing. This is very important. You know, as I mentioned before, the method that I teach you here is applicable in real world industrial problems with large dimensions. Okay? Here we take a 2x2 case just to learn to walk before one can run. Right? So that's, please keep this in mind. So once you notice that, then the decomposition or the diagonalization of the stiffness matrix can now take a very nice form. That's K equal to, right, you have phi bar, because now we use the normalized matrix of the eigenvector, and then the diagonal matrix lambda of the eigenvalues, and then you have phi transpose. You no longer need phi inverse, phi bar inverse, but you can use phi bar transpose and save a lot of computational time. Okay, very good. So now, how do you solve the problem KD equal to F? Remember the original problem? The original problem that we wanted to solve is KD equal to F, right? And that's that is shown here. Let me zoom out so that you can see the big picture. This is the original problem here, right? That's the simple example, and this is the stiffness matrix. This is the applied force matrix. The displacement is just inverting this matrix times the force matrix, and then you get the displacement, right? And you say, well, you know, this is so simple. So why did we go through all the hoopla, you know, of matrix theory and eigenvalue problems and inverse, and just to solve this simple problem? No. What we're doing here is a motivation to solve a much more difficult problem, not this simple problem. In statics, you can just invert directly and multiply by the applied force. But what I'm preparing you is to solve the dynamic problem. Okay, remember the two coupled ODEs. That's really our goal. Okay, so even then, how do you uncouple this system? So here is how you do. And this is directly in preparation for the next lecture notes there. So what you do is you replace K by its, the decomposed form. Okay. So let me put down here, and let me replace K by this one, right? So this matrix here is the stiffness matrix. Okay. Now you introduce a new variable called y, and define y to be, and I use exactly the same variable that you will see in ODEs. Okay, so you define y to be this. what I want is not this one, but I want the displacement. Okay. So this is a new variable y, the new unknown y. It's a matrix defined to be that. Okay, and you pre-multiply, meaning multiply from the beginning. Pre-multiply both sides by phi transpose. Okay, so now what you have is take phi transpose, right? Multiply by phi bar transpose multiplied by phi bar and lambda, right? Lambda is, sorry, I need to copy the whole thing. Okay, and we have already defined phi bar transpose d as a new variable y, so this is y, right? This is multiplied by y. Okay, and then on the other side, you would have phi bar transpose times f. Right? Multiply both sides by phi bar transpose. Now here's the magic. What is phi bar transpose times phi bar? Active learning credit? Kevin?
It's 1.
Identity. Very good. Because we just show that the inverse of phi bar is phi bar transpose. So phi bar transpose is phi bar inverse times phi bar. That's identity matrix. So let me note Kevin, team 7 is very active today. That's excellent. Okay. So here, let me copy this over here so I have more space. And like we said, or Kevin said, that this phi bar transpose times phi bar is the identity matrix. And let's define phi bar transpose times the applied force F as a new quantity and use it in the same variable that you will see in ODE R for the right hand side. So watch, what you have left is this. Okay? What you have left is this. You know, we have a new definition now, so we can get rid of that. That's it, right? This is a new, R is a new applied force, Y is a new unknown in the new coordinate system, the coordinate system of the normalized eigenvectors. Lambda is a diagonal matrix, right? Whenever you have a diagonal matrix, the solution is very, very simple. The two equations had been uncoupled already. Wow. You can write out the detail and you see lambda is lambda 1, lambda 2, right? 0, 0 times y1, y2. That's the column matrix. Y equal to R1, R2, right? So therefore, the two equations are now completely uncoupled. The first equation is lambda 1 times y1 equal to R1. And therefore, you can solve immediately y1 equal to R1 divided by lambda 1, right? Lambda 1 was equal to 1, okay? R1 you can find easily, right? Because R is a phi bar transpose times F. And you know phi bar transpose, so you can, and you know F, you know what I meant is the following. Let me zoom out so you can see the big picture, right? R is phi bar transpose, and F is the applied force. Both matrices are known, so that you can compute R easily. So the numerical values of R1 and R2 are known. The numerical value of lambda 1 was 1, so therefore you can find the numerical values of Y1. And the same thing for for the second solution, or the new displacement, if you like. You know, the displacement in the new coordinates. So you just get rid of all of the subscript 1 and replace by 2. That's all that is. Right? Because the two equations are completely uncoupled, meaning that they don't depend on each other anymore. And so the index now 2, lambda 2 y2 is equal to r2. There's no r1, sorry, no y1 in this equation. So therefore y2 is equal to r2 divided by lambda 2, right? Lambda 2 was 3, equal to 3. And r2 is what you can compute by multiplying phi bar transpose times f. Any questions? Difficulty? Remember, asking questions you get active learning credits too. Doesn't matter what question. Okay. Anyone who needs me to repeat? So this is it. This is the model of diagonalization. This is how diagonalization is important, because remember, this is simple in the case of static, but in the case of dynamic, if you can diagonalize the two coupled second order ODE into two scalar ODE, the solution of the scalar second order ODE, you already know how to do it. Okay, at least for simple excitation. That is considered as prerequisite and reviewed in my extra lectures. All right. So, so we move on. We move forward. Feel free to ask questions, even on things that I had done before. So we have done all of this. All of this part is done in this section here. Now we move to this section. I apply the idea that I just described to now really solving the coupled ODEs, right? Second order coupled ODE, and that's section 53D. And I have noted down some critical thinking questions, but I will come back to that later. Okay. I'd like to move forward to section 53D. Okay, so here is section 53D. Let's zoom out. All right, so I have already, by the way, what I do here in the first, I will.
I'm doing a nice problem right now.
If you look into the weekly lecture summary, maybe it's important to give you an orientation. In case that you need to have further reading, if you go into the weekly summary, which can be accessed through the portal. Right, you go into the portal and you go into the weekly schedule, where I have listed week by week the lecture notes, as well as additional references, and here you would notice that for example, in the first half of the semester, we essentially do 3 chapters in this book, Kelly 2011. So we cover a lot, even just in the first half of the semester. Okay, I'll probably send out the email so to show you more detail. But this is just to for you to keep in mind. Let me zoom in here to fit. Yeah. So for example, I noted down here, chapter 6 in Kelly is about the 2-degree freedom system. I also give a new reference by in my 2013 different chapter numbers, and then chapter 8 and chapter 9 will be things that we will address. Okay, so let's go back to here. So this is a new topic. The first topic, remember, was derivation of the equation of motion, right? Through free body diagrams. That's the first topic. Second topic was undamped free vibration. Okay, with the undamped free vibration, you can obtain the generalized eigenvalue problem. So now the third topic is actually fourth topic, because third topic was what I just explained when I wrote. That's the standard eigenvalue problem, and now generalized eigenvalue problem. Okay, so active learning credit for a review, a quick review for the class. Anyone? What's the difference between standard eigenvalue problem and generalized eigenvalue problem? This is a review. We went through this already. The value?
Is it that M is the identity?
Yes. Yes. When M is an identity matrix, that's called the standard eigenvalue problem. Right? The generalized eigenvalue problem is more general and includes the standard eigenvalue problem as a particular case. So I said in some lectures ago that if you know how to solve the generalized eigenvalue problem, you know how to do the standard eigenvalue. It's the same method, simple for the standard eigenvalue problem, and we'll get there. I give examples. Okay. So we have derived this expression from looking at the undamped free vibration, where the matrix K is the stiffness matrix, the matrix phi is the matrix of the eigenvectors, beta is the eigenvalue, M is the mass matrix, and phi is the eigenvector. When you solve this, you will have two eigenpairs, two eigenvalues, two eigenvectors. Okay. And I even give the equation here. This is equation 3 on page 53-27. Right? That's the previous lecture notes. Okay, so now you can move the right-hand side to the left, and you can write matrix K minus beta times matrix M, the mass matrix, times the eigenvector phi equal to 0. Okay, this is a 0 matrix. What's the dimension? What's the dimension of the matrix 0? Well, I give Devane team 6 active learning credit. Please think or discuss with your teammates. What's the dimension of the matrix 0? 0 is not a scalar, right? It's in bold faces. This is a bold face 0. It's not a 0 scalar. It's a matrix. What's the dimension of that matrix?
Is it 1 by 2?
2 by 1.
2 by 1.
2 rows, 1 column. Very good, Maria. Okay, Maria is team 8. Yes, it's a 2 by 1 column matrix. Okay. Why? Look. K minus beta M is a 2 by 2. Phi here is a 2 by 1. So a 2 by 2 times a 2 by 1 is a 2 by 1. Right. Now the reason that you put the generalized eigenvalue problem in this form is as follows. Remember that there are 2 unknowns, right? Beta and phi are 2 unknowns. Now, to solve for these 2 unknowns, this is how, this is the first step here. This is the argument here. Suppose that this matrix K minus beta M was non-singular. Non-singular means that the determinant is not equal to 0, right? If the determinant is not equal to 0, then the vector phi would be 0, right? Because the right-hand side is 0. You can just invert this matrix, and therefore phi has to be 0. So the only case that phi is not equal to 0, meaning non-trivial, right? For the eigenvector to be non-trivial, you want the determinant of the matrix K minus beta M to be 0. Is this a scalar or a matrix? Active learning credit. Is this 0 a scalar or Kyle? I know you have contributed. Kevin already contributed. So let me bring David. Okay, please continue to be active. David, scalar. Yeah, very good. I'll pick you next time. Please raise your hand. So David is what team? Team 2. Okay. Team 2. Right, so the 0 here is a scalar, not the matrix. Okay, very important. Keep in mind this argument, this reasoning, why you want the determinant equal to 0. Now look, you see this condition here have already reduced the number of unknowns, because here, how many unknowns you have here? You have 3 unknowns. Beta is a scalar and 2 coefficients in phi, right? 3 unknowns. How many equations? How many equations here? Active learning credit. 2 equations. What's your team number and name? Team 6. And your name? Your name? Dylan. Oh yeah, Dylan. Okay, Dylan had contributed. Okay. Where is here? How many equations and how many unknowns?
One equation, one unknown.
Maria?
One equation, one unknown.
One equation, one unknown. Okay. One equation, one unknown. Very good, Maria. So now we are in the business of solving for beta, right? That's it. You just replace, right? Express K minus beta M in fully expanded form. You have K11 minus beta M1, because remember M is diagonal. So in the 1,2 coefficient, you have only K12 because M12 is 0. So beta times M12 is 0, right? So you have only K12. And likewise down here, K21, row 2, column 1, you have only K21. And in this 2,2 position, row 2, column 2, you have K22 minus beta times M2. And replace the numbers in, K11 was 14, M1 is 2, so beta is the unknown. Look at look at the 2,2 coefficient. K22 was 3, M2 was 1/2, and beta was unknown. And the off diagonal coefficients for the stiffness matrix, K12 equal to K21 equal to minus square root of 6. Okay, so, and you just compute this determinant, set it equal to 0. Well, the product of 2 diagonal coefficients minus the product of 2 off diagonal coefficients give you a quadratic equation in beta, right? And so what that is, let me zoom out so that you have the big picture. And so the big picture is now, this determinant okay. This determinant is a quadratic equation. You can multiply out, you can see that it has to be a quadratic equation in beta. So when you solve these quadratic equations, you have two roots, right? 2 solutions. So these are the 2 eigenvalues. Okay, beta 1 and beta 2. And you see, by design, I told you by design, I selected seemingly complicated coefficients so that in the end I have very nice roots. These are exact square of some simple numbers. If you solve this, you will see that beta 1 will be equal to 4. And you recall that beta 1 is the square of omega 1 from previous lecture. Then omega 1 is equal to 2. Omega 1 is called, one more time, the circular frequency of vibration. And I'll have an opportunity to give you a physical meaning of the circular frequency. Yes.
Is circular frequency the same as angular frequency?
Yeah, angular velocity, sometimes maybe called angular frequency, but I'll get there, Anderson. Okay, this is excellent. I'll give you credit on this. And beta 2 is equal to 9. Thank you. And beta 2 is the square of omega 2, and C omega 2 equal to 3. So you see, I solved the inverse problem, came up with the coefficients that had all the square roots, and in the end, so that I can come down to just very simple integers. Okay, so let me vote Anderson down, and that's team 6, right, Anderson? Team 7. Okay, so let's see here. I saw the signal from our friend. I still have 5 minutes, so let me address Anderson's remark immediately, so that way this is a good time to wrap up. So here is how you would remember without memorizing the concept of the circular circular frequency of vibration. Think of a circle where you have the and this is the radial direction, and it is rotating around with an angular velocity omega. Okay, and so the angle is, you can call this angle theta, is equal to omega t. Okay. Now, so think of this radial direction is keep rotating, right? Omega is a constant called the angular velocity. So as time t increases, it's just rotating. So you see, it's a periodic phenomenon, right? So when the radial direction starts from 0, wrap around, when it finishes 2 pi, that's 1 period. So what is a period? A period is when theta equal to 2 pi. So you write 2 pi. Let me move this to the right hand side. So on the left hand side, you would have omega times gap t, or maybe let me use the notation p for period. Gap t is also frequently used, okay, in vibration. Okay, that's it. So now this is the relationship between the period and the angular frequency of vibration. So therefore you have from here omega is equal to 2 pi or 2p over p. Okay, 2 pi over p. P is a period. I'll get into the dimensional analysis later, but at least here that gives you a simple way to remember the definition of the angular frequency of vibration. Okay, so please, lecture summary.
Where do we normally put this? Where do we normally put this?
Give it to him. Just hand it to him.
Yeah, you can put here so I don't forget. Yeah, thank you.